All right, welcome everyone. Welcome to our newly established seminar series on optimization, algebra, and geometry. Today, we are pleased to have Tim Duff from University of Washington. Tim is working on computational and numerical algebraic geometry, and he's going to talk about an atlas for pinhole camera. Tim.
Great. Yeah, so thank you to Ali for the invitation to speak today. So I'll be talking about this recent paper that I wrote with some people who are affiliated with the University of Washington. So these would be my co-authors, Sameer Agarwal, Max Lieblich, and Rekha Thomas. And Sameer is also mainly working at Google. And this is basically going to be a mathematics talk, but one which is largely motivated by questions from computer vision. And so the title is called An Atlas for the Pinhole Camera. And we were just talking about what is the meaning of the word atlas here. And it's sort of an informal word, but it refers to a collection of interesting algebraic varieties that appear in the study of perspective image formation, also known as the pinhole camera model. And the picture that you see on the very front slide is this atlas, which sort of some arrows indicating operations which take you from one variety to another. And so what I'd like to do in this talk is maybe motivate why would you be interested in studying such a thing in the first place, and hopefully be able to at least state main results at the very end. But I do want this to be as interactive as possible if you have any questions, so please don't be afraid to interrupt me at any point. There's already too many slides for me to get through, so I'll try to go slowly in the beginning before telling you what our results are. Okay, so as I mentioned, computer vision is the subject that really motivates this work. And there is just a huge amount of work that, okay, if you haven't been living under a rock for the last 10 years, then you probably know that computer vision is concerned with object recognition and tracking and 3D reconstruction. But it's also concerned with geometry, which is particularly relevant to the 3D reconstruction part. And in fact, the relevant geometry often turns out to be algebraic geometry. And this has been understood for quite some time. And there's a huge amount of work that we are sort of building on. And in particular, I'm going to tell you something about what people usually refer to or often refer to as multiview constraints. And just in case you're curious and want to go read something later, I can tell you about two references that are relevant here. So one would be this book by Hartley and Zisserman, sometimes called the Blue Book. Its title is, let's see, Multiple View Geometry. And there's another book that deals with very similar topics called Invitation to 3D Vision. By Yima and a few other co-authors whose names I don't recall. And they are both kind of addressing basic questions of what are the fundamental constraints that one sees when studying simple but surprisingly useful models in computer vision, like the pinhole camera model. And I'll tell you about how to think of these in an algebraic geometry context and some things that we proved that were perhaps surprising in view of people's previous work on these multi-view constraints. And another thing that makes algebraic geometry useful in this subject is that it actually leads to some algorithms that are relevant for solving 3D reconstruction problems. And it's not the focus of this talk, but I'll give you a few buzzwords. So probably the most prominent example of an algorithm that's algebraic geometry based in computer vision is this thing called the 5-point algorithm. And this is due to Mr. And more generally, there's a collection of techniques that are used in 3D reconstruction pipelines called minimal solvers. And what the 5-point algorithm is really a special case of this minimal solver world. And they both rely on Groebner basis computations, which is perhaps a little bit surprising if you know anything about Groebner bases, because they have such high computational complexity in a general setting. But for very specific problems, the structure is well understood enough that people can do things very efficiently. So these are just two examples of why algebraic geometry is relevant to computer vision in practice. But as I said, this is more of a mathematics talk, and so I'll be focusing really on these multiview constraints and what more can we say that hasn't already appeared in a rather large literature about this subject. So basically, in our paper, which appeared on the archive a few months ago, we're suggesting a framework that encompasses a lot of the previous results. And I think from this point of view, which is the main thing I'll be telling you about, we were able to prove a lot of the previously known results, but also find some surprising things that apparently hadn't been noticed before. Now, just to tell you a little bit more on this idea of algebraic geometry being relevant to computer vision, let me introduce the components of the Pinhole Camera model to you. Basically, in this model, there are always going to be 3 components. So usually what's given to you in most applications would be some sort of image point. And so P1 and P2 here, you can think of as being pixel values. And how exactly do these points come to you in an actual image? Well, there's a whole bunch of image processing that tries to look at patches and gradients and say, this is a point that might be, reflecting an actual point on a 3D object somewhere in the world. But for us, this is just some geometric entity. And we write it in homogeneous coordinates. Because, it's well known that these are useful to people coming from computer vision and computer graphics. And the Pinhole Camera is, in some sense, the reason why it's useful. So this is usually something that's given to us. What we don't know, if we're just looking at images, is the associated world point. Now, I've written the world point as a scalar multiple of this image point in homogeneous coordinates. And the reason I can do that is because I'm working in the frame of a camera, or what I'll call the camera coordinate system. So this is a very sort of conveniently chosen coordinate system in which that allows me to express the world point as a scalar multiple of the image point in homogeneous coordinates. So I've chosen the camera center to be the origin. And the image plane, so if P1, P2, P3 are coordinates in the world, is basically given by P3 equal to 1. And so this is projection through a point onto a plane, and the choice of coordinates is what allows me to say that the world point is some scalar lambda times this image point. And lambda I would call the depth of the point in the image. So these are just the components of the pinhole camera model, just to fix some terminology. And using this figure, I'd like to explain to you what's so algebraic about computer vision. Well, the point is that this projection map that takes a 3D point to the 2D point is not a linear transformation, but a projective linear transformation. So this world point to image point map, well, let me write the world point in homogeneous coordinates as well. So append a 1 to this 3x1 vector lambda times p. And so from the world point lambda times p, I obtain the image point, which is just p. And essentially what I'm doing is just forgetting this last coordinate 1, which is the same as multiplying on the 4x1 vector here on the left by a 3x4 camera matrix, whose left 3x3 block is the identity and rightmost column is 0 vector. That will just give me lambda times p, however. And so in order to get the image point back, I have to rescale by this depth lambda. So this is what I call the linear algebra version. And the algebraic geometry version is not much different. It just works in projective space. So once again, I take my world point in homogeneous coordinates and map it to the image point in homogeneous coordinates. But now, since I'm working in projective space, I can just forget this lambda here. So by definition, a point with these homogeneous coordinates, lambda p1, lambda p2, lambda, is the same as the point p1, p2, 1. But this assumes that the lambda, the depth of the point, is non-zero. And so the image that you get, if lambda is equal to 0, well, basically that means that you'd be imaging the origin, and there's no way to draw a line from the origin to itself, or there are too many ways to do that. And so actually the image of this perspective projection is undefined at the origin. And when I write a dashed arrow here, that just means that this is a map. So in the linear algebra version, we have this sort of nonlinear transformation of linear map.
There's a question from Jeff in the chat box.
Okay.
He's asking, where did the extra dimension come from?
So what I'm doing is I'm taking, yeah, good question. So you're talking about this 1 here on the world point, or some other extra dimension?
Yeah, there's an extra 1 there.
So this is taking the world point and writing it in homogeneous coordinates.
So I guess I'm similarly confused about why the world point has only 2 coordinates.
The world point has 3 coordinates.
Okay, so there's a P1, there's a P1, P2, P3. Okay.
Right. So I mean, there's this scalar lambda, which is giving you the 3rd degree of freedom, basically. So
okay.
Yeah, maybe.
But so when you talk about P is the world point?
P is the image point.
P is the, okay.
Perhaps not so clear, but this here is P, and this here is also P.
Okay.
And since it's in the image plane, its last coordinate is equal to 1.
Got it.
Okay, so the punchline of this is that we have a way of thinking of the camera in terms of some linear algebraic object, which is just, we take a point in P3, which I could write, I could think of this as a 4x1 vector here, and think of this as a 3x1 vector here, and it's just matrix multiplication. But there's a catch here, which is that it's matrix multiplication where I'm allowed to disregard scale. And so for one camera, it seems that by working over the projective spaces, we have a magic way of turning this nonlinear transformation into a linear transformation. But there's a catch when you start looking at multiple cameras, which is that things suddenly become nonlinear. Okay, so yeah, any more questions I can answer to sort of clarify this?
No, I'm good.
Okay, great. So moving right along. So when we wrote down the camera coordinate system on the previous slide, we were making a lot of convenient choices. In general, there are many coordinate systems in play. So there will be a camera coordinate system, which we saw before. And I'll allow a camera matrix to be an arbitrary 3x4 matrix. So that means it has 12 entries. And if I regard it up to scale, then I can think of it as an element of 11-dimensional projective space. And similarly, the world point will be in projective space P3, and the image point will be in the projective space P2. And so you might wonder about, okay, I know the world is 3-dimensional and the image is 2-dimensional, but what about the camera? Is there some interpretation of this number 11? And there actually is. It's that 11 equals 5 plus 6. And 6 counts sort of rotational and translational degrees of freedom for the camera. And 5 counts the degrees of freedom involved in an affine transformation with the image. These are sort of like some internal parameters of the camera. But the point of this slide is just to make you not so nervous about taking the leap from this very special camera matrix I0 to an arbitrary 3x4 matrix, which I'll be denoting by A. And so the main question that we wanted to answer in our paper is, what is a complete set of constraints that applies, that fully describes the geometry of an arbitrary set of cameras, world points, and image points, and where the number of cameras can be arbitrary and the number of world points can also be arbitrary. And we have some sort of answer to this question, but the point of this framework is really to try to uncover different ways in which you could ask that question. And the reason why it's interesting to consider different ways of asking this question is because in practice, you could be given different measurements depending on which problem you're trying to solve. So the motivating applications here are basically what are usually called triangulation and resectioning. And then there's sort of a full reconstruction problem. So in triangulation, this is a fairly well-studied problem. We're given M cameras, and I'll be using a bar over each quantity to indicate that it's given to us. This will be very important notation later. So in triangulation, we're given cameras, and we're also given images, P11 bar through PMN bar, and our task is to recover the world points. Now, resectioning is sort of...
why is it called triangulation?
Why is it called triangulation? Well, the idea is that if you know this image point and this image point, and you know this camera and this camera, then to get the world point, you are intersecting these two rays, and generally they'll intersect in a single point. And there's a third line here too, which is actually connecting the camera centers. And there you have a triangle. So the idea is that you need 2 line of sight observations in order to localize an object in the world, at least generically speaking. So that's triangulation. And resectioning is sort of a mirror version of this problem, where instead of being given the cameras, you're given the world points. And now, maybe you're drawing triangles that try to help you determine what these camera centers are. And from that, hopefully recover the camera matrices themselves. But the holy grail of this subject is really sort of full reconstruction problem in which you're given only image coordinates, and your task is to recover both the cameras and the world points. And this is a very challenging nonlinear optimization problem for a number of reasons. And there's a lot of engineering work that goes into building solutions that really do practical things. But I would say that, like, on an algorithmic level, there's a lot that still people don't really know about this problem. And so being able to say something about what is a complete set of constraints for any one of these problems is the grand challenge that motivates our work. And we are able to say something in a precise sense that applies to each of these problems. But I have to tell you what a complete set of constraints means. And I think within 7 minutes, I can probably get there. So maybe just to show you why we have something nonlinear occurring here, let's consider an example that comes from triangulation. So remember here, I'm given a camera arrangement. So M cameras, A1 through AM. And I'm going to study what kind of image points I can get from a world point Q. And I have a map from P3 into the image space P2 to the M, where M is the number of cameras. And the triangulation problem is basically asking me to invert this map. So a simple example, let's say that one camera matrix looks like a 3x3 identity block on the left, and another camera matrix looks like a 3x3 identity block on the right. Then I claim that the image points that I get have to satisfy this quadratic constraint. And this is a pretty easy calculation, so let's just do it. If I take my given camera matrix A1 times the world point Q, and let me just write out the coordinates of Q as Q1, Q2, Q3, Q4, then I'm saying, okay, that should be equal to some point in P2, the first image, P11, P12, P13, but it's equal up to scale. So there's actually this depth, m to 1, that makes this equality true. And in projective space, we can sort of ignore this depth, and you might think that, okay, well, isn't this map just sort of taking Q to some sort of block matrix times Q, like A1 bar Q, A1 bar over A2 bar times Q? Well, the answer sadly is no, because there's each camera, the depth of the world point is different with respect to each camera. So that if I write out A2 bar times Q, then what is that? Well, there will be some other depth, lambda 2, times the coordinates in the appropriate image, P21, P22, P23. And the point is that lambda 1 and lambda 2 could be different. However, I can still describe some relation that must hold on the image coordinates, regardless of what the scalar factor is. And the way I do it is I look at a ratio. So if maybe it would be helpful to write out what A1 bar times Q is. Well, that's just going to be picking out the first 3 entries of this vector Q. So Q1, Q2, Q3. And for A2, it's picking out the last 2 entries, Q2, Q3, Q4. And if I look at what's in common here, well, on both sides, I have Q2 and Q3. Sorry, here I have Q2 and Q3 on the top, and here I have Q2 and Q3 on the bottom. So if you look at the ratio of Q2 over Q3, what you'll get in terms of the image coordinates is lambda1 times p12 over lambda1 times p13. That's coming from the first image. And coming from the second image, I'll get lambda2 times p21 over lambda2 times p22. And now the important point is that these lambdas cancel. And if I cross multiply this whole thing, I'll get this quadratic constraint that needs to hold among the image coordinates. So in fact, the image of this triangulation map for a given set of cameras is not a linear space, but it's defined by this single multilinear equation. And this is the simplest example of what's called a two-focal constraint in our paper, also known as a two-linearity in other parts of the vision literature.
So physically, does this correspond to just one camera looking straight ahead and one looking straight up or something like that?
They could be looking in, yeah, they should be looking in directions where the centers are not the same, basically. Okay. If that's the case, then up to the natural action of world and image coordinate changes, you can always reduce to these specific camera matrices. So they look specific, but their orbit sort of generates everything where you don't have two cameras on top of each other. Okay, so let me get to the definition. The image formation correspondence is a geometric object that captures everything that we're interested in. So for any choice of m cameras, n world points, and mn possible images, we look at the incidence conditions imposed by saying that qj maps to pij under ai, and this gives us some Zariski open subset of this product of projective spaces. And if to talk about functions vanishing on this Zariski open subset, it's equivalent to talking about functions that vanish on its Zariski closure. So this big bar is saying take the Zariski closure, and the task is to determine all equations that can possibly vanish on this multi-projective variety. And without getting into it too much, what we call the atlas is a network of algebraic varieties that are somehow emanating from this image formation correspondence by geometric operations, namely projection.
Sorry, I have a question.
Sure.
So why are we taking the closure here? Isn't it a projective variety already? So
well, not necessarily.
Do you have any example that this is not necessarily a projective variety?
Sure, and even in the simplest case where m and n are both 1, it won't be a projective variety.
Okay.
The reason why that is because, like we saw on the previous slide, this matrix product could be 0, which means that it's undefined.
Mm-hmm.
So, but you could imagine a sequence of cameras and world points that is converging towards a configuration where this matrix product is equal to 0. In fact, it's really simple. Take your favorite camera and then take a sequence of world points that converges towards its camera center. That will appear in the limit when you take the Zariski closure.
Okay.
So yeah, taking the Zariski closure is necessary to get a projective variety, but it's harmless in the sense that it doesn't change the set of functions or really homogeneous polynomials vanishing on it. Okay, so just to briefly state the main results since we're over time, there are all these varieties that one can obtain from the image formation correspondence by projection or setting some particular quantity equal to, like basically saying, okay, my camera arrangement is going to be fixed. That will give us some analog of the triangulation problem. And in geometric terms, we're projecting or taking coordinate sections of these varieties. And with this atlas, you can sort of do fun things like count dimensions. But the main theorem is really saying, what is the vanishing ideal of each of these varieties? And our strongest results apply in the case where we have a single world point. And in that case, we can say that the vanishing ideal, which is just the ideal generated by all multi-homogeneous polynomials vanishing on this variety. For the image formation correspondence, this vanishing ideal is the sum of two ideals. One is generated by all 2x2 minors of matrices of the form AI times QJ as the first column and PIJ as the second column. So this is a 3x2 matrix. And I have one for every camera. And it's sensible that this sort of thing should vanish because after all, AI times QJ is equal to some depth lambda ij times Pij. So this minor should vanish. This matrix, this 3x2 matrix has rank 1 and all these minors should vanish. But actually these minors are not sufficient to generate the vanishing ideal. There's an additional summand that comes from constraints that only hold on cameras and images. And these correspond to things that are well known. We call them 2, 3, 4 focals. I showed you a 2 focal on the previous slide. There's a lot more to say about them. And this gives us 2 vanishing ideals in the case of a single world point. What can we say for more than one world point? It's a little bit more complicated. What you would like to be true is that you can just sum all of these ideals over each individual world point, and that will give you the vanishing ideal. But it's actually not true. There are simple examples given in our paper that say that this sum of ideals will be a proper sub-ideal, the whole vanishing ideal. So it's not a complete set of constraints. However, if we perform an operation of saturating by the set of minors of sort of a stacked camera matrix, then this will allow us to obtain the full vanishing ideal for any number of cameras. So it's actually a pretty weak result because computing saturations is non-trivial. But in some sense, the most we can say because this saturation step is actually necessary for a very small number of cameras and world points. And so this is just one of the few things that we proved in the paper. One final highlight I'd like to show is there's this nice result of Aholt, Sturmfels, and Thomas that says that for the triangulation ideal, these focals that I alluded to earlier form a universal Groebner basis for the ideal that they generate. And I think we have a fairly simple proof of why that's true. And it comes from looking at another variety in the atlas and first saying something about its vanishing ideal. And so these are just some of the results you'll find in the paper, but hopefully it intrigues you to look forward into it more closely. And yeah, that will be where I stop. So happy to take questions.
All right. Thank you, Tim. Let's thank the speaker for this fantastic talk. So we have a couple of minutes for questions, basically 10 minutes or so. So maybe I can start the questions. So do you have any computational results? Do we know how to find the Groebner basis? I mean, what is the complexity of computing the Groebner basis for this corollary here? Or we just know what the basis is? Do we also know how to compute them?
Oh yeah, I mean essentially you're asking what are these polynomials then?
Exactly. Yeah. How do we compute them? I mean, or if there is a way to compute those polynomials, what is the complexity? I mean, is there any result on this?
Well, I mean, I can tell you in concrete terms what they are, and then maybe you can infer a complexity theoretic statement from that. So how many of these polynomials are, so they're all minors, which are, let's say, 6 by 6, 7 by 7, or 8 by 8 of some matrices of fixed size, let's just say. And the number of them depends on how many cameras you have. So there are m choose 2 of these 2 focals. There's 27 times m choose 3 of the 3 focals, and there's 81 times m choose 4 of the 4 focals. So basically, if you are content with computing determinants at some fixed cost, then this tells you how many determinants you need to compute. And we know what the Groebner basis is due to this theorem. So there's no like funny S polynomials that you have to compute.
Mm-hmm. And what do you mean by the arrangement? So to me, it sounds like a generic result, right? So we have some sort of genericity assumption here. Is that correct?
Absolutely. So the genericity result that's needed to show that we have a universal Groebner basis is that these given cameras are such that all of their 4x4 minors are non-zero. So that's a seemingly strong genericity condition. But it's closely related to this thing we were talking about before, where you don't want 2 cameras like on top of each other. So you want the camera centers to be distinct. In fact, up to the group action, if the camera centers are all distinct, you can apply a transformation so that this genericity condition, which I guess you could call minor genericity, is satisfied.
Right, but I mean, like for some problems, I saw in the papers that they think of the result for the under genericity as an upper bound for worst case scenarios. Can we have argue the same thing here? So you have some results under generic conditions. Can we think of it as an upper bound under worst case scenarios?
I would say no. The reason being is that when you start considering very special scenarios like 2 cameras on top of each other, new constraints appear. Like, so for instance, if I have 2 cameras facing the exact same direction, then image point in one, a point in one image plane and a point in the other image plane have to lie on the line that they span with the camera center.
Mm-hmm.
And that's not something that holds in generic situations. So really, what's happening here is you have a family of these multiview varieties, and it's captured by this other variety in our diagram, which we call gamma AP, sort of a universal multiview variety. And there's a Zariski dense locus of cameras within this family where all the multiview varieties look the same. I mean, that's sort of what this Aholt, Sturmfels, Thomas result is telling us. And it's basically the flat locus. So flatness in the sense of algebraic geometry or commutative algebra. And once your cameras, if your cameras are in this flat locus, then all the multiview ideals look the same. And if they're out of the flat locus, then you're in this cameras on top of each other situation.
Mm-hmm.
So because new constraints appear in non-generic situations, it's probably not fair to say that this is a worst case bound in any sense that I can think of.
All right, great. Any other question?
Well, I'll ask a kind of a vague, open-ended question. So over the summer, I met somebody who from Israel who used to do 3D vision And he told me that the field is basically no more because machine learning, all the problems they thought were hard, machine learning just takes care of. And even if you go and you think, okay, I know something that machine learning doesn't, and I'm going to adjust and tinker with the algorithms, you invariably make it worse. But is there some kind of interface? I mean, is there some way of combining, algebraic, precise representations with the machine learning? I mean, you can get machine learning to learn algebraic representations that you can then use.
Yeah, so there's a huge amount of work with people like sort of combining learning and vision. And in fact, I even have a joint paper that addresses this very topic. But there are many angles that you could consider. Like one would be, using some domain knowledge to pre-process the input, which sort of goes against this orthodoxy of like, you should never hand engineer anything. But you could also use learning to try to speed up some of these 3D reconstruction algorithms. And so learning has had a huge impact from my vague understanding on basically every part of the pipeline used in 3D reconstruction. But a lot of the geometry algorithms from the 90s, let's say, are still in use. So I think that there are a lot of ways of combining geometry and learning, and people are definitely doing it. But at the same time, I don't think that the geometric methods have completely fallen out of use.
Thank you.
All right, any other question? All right, if not, let's thank the speaker again for this fantastic talk, and thank you all for coming. And hopefully I will see you next week with our second speaker. Well, thank you very much and have a good day.
Great.
Thanks a
Thank
lot.
you, everyone.